Welcome back. We continue with some exact solutions on Navier-Stokes equation. We had done the Poiseuille-Couette flow in the last presentation. The Poiseuille-Couette flow is the flow of a liquid between two parallel plates, one plate being stationary, the other plate moving with a constant velocity v naught, and an applied pressure gradient along the length of the tube. We assumed the flow to be steady, incompressible, fully developed and one-dimensional. Under these assumptions, we showed that there is only one component of velocity Vx, which we denote with u, and it is only function of y. Since the flow is fully developed, there is nothing that depends upon x. The velocity profiles was shown to be like this for the various values of the pressure coefficient. Non-dimensional numbers. When there was no pressure gradient along the tube, then the profile was a straight line profile. For negative pressure gradients, the velocity profiles are like this and this. For positive pressure gradient, that is the pressure increasing downstream, the velocity profiles are pushed back, this and this. When the pressure coefficient has a value of 2, you notice here that there is large depth of the flow across which the velocity is negative. Is only in this portion near the upper plate that the velocity is positive. The profile with the pressure coefficient of plus 0.25 has a special value, and that is the shear stress at the lower plate is 0. Delta u by delta y is 0 at the lower plate. Let's apply this flow to a problem of thrust bearings. If we had a propeller shaft which was rotating a propeller of a boat, we would need bearings so that the propeller shaft could rotate. But this propeller shaft would produce a thrust. Because of this thrust, the propeller shaft would be pushed back. And this would need a restraining device while the propeller is running. And this is provided by what is called a thrust bearing. This is the thrust bearing which permits the shaft to rotate easily with very low friction while resisting the axial force. One of the common design of a thrust bearing is a Mitchell tilting pad bearings. This works on the principle of Couette flow. It consists of a number of pads like this, which are pivoted in such a manner that when the axial load comes on this and they are rotating, the pad is rotating in this direction with an angular velocity omega, so that the linear velocity is omega r. If r is the radius at which the pad is attached, then it adjusts itself in such an orientation so that the lower surface is tilting. And now the lubricating fluid is pushed across this in this direction. It forms a channel which is a converging channel for the flow. Let's analyze this. For analysis, tilting is a little more complex, so we convert this into a stepped channel. So the tilt is replaced by two flat areas, AC and CB, so that the first part is a channel of width B1 and the second part is a channel of width B2. Let both of them have equal length, L by 2 each. This is a quasi one-dimensional approximation. We assume the flow through each channel to be one-dimensional. Obviously, at the center, the assumption would break down and this would be quite complex. If the length L is much larger than the width B, then this approximation could work. Now, we assume that a pressure gradient is created in this channel in such a manner that the flow through each part of the channel is the same. In a steady state, the flow through part 1 of the channel should be the same as the flow through part 2 of the channel. Q1 dot prime should be equal to Q2 dot prime. The prime indicates we are talking of per unit depth. Now, clearly, Q1 dot prime should be equal to Q2 dot prime. The pressure at point A and pressure at point B are atmospheric and so equal. And the pressure at point C should be continuous. That is, pressure at point C in the first part, just before point C, should be equal to pressure at point C in the second part, just after the step. With these conditions, now we have derived in the last presentation the volume flow rate per unit depth is B V naught minus twice P prime B cube by 3 mu, where B is half width of the channel and P prime is the pressure gradient along the length of the channel. Mu is the viscosity of the fluid and V naught is the speed of the upper plate. Now, for the two parts of the channels, AC and CB, we can write the values of B, V naught and P prime to be used in there. B is equal to B1 by 2. The half width of the channel is B1 by 2. For the part CB, it is B2 by 2. V naught in both cases omega r. P prime, the pressure gradient in the first part is PC gauge divided by L by 2. The pressure changes from 0 to PC gauge in the length L by 2. For the conditions of co-ed flow, this pressure gradient is independent of the x variable. So we can simply write P prime as PCG divided by L by 2. For the second part of the channel, that is part CB, the pressure gradient would be same but with the opposite sign, minus PCG divided by L by 2. We can find out the values of the flow rate q dot prime in 1, and we can find out the value of q2 dot prime for the second part and equate the two. All variables have the known value except for PCG. So this way we can evaluate the value of PCG. Once we evaluate the value of PCG, we can evaluate the vertical force that it can support. The pressure in the first part AC is rising from 0 to PCG, and the second part the pressure is decreasing from PCG back to 0. So pressure acting on the part AC varies from 0 to PCG. The average pressure is PCG divided by 2. And so this is a force per unit length that we found. It is not 2, it should be 4. PCG divided by 2 into L by 2. The total force that we evaluate comes out to be this. This is the total thrust that this bearing can support when gap B2 is 1/2 of gap B1. To calculate the lost power by this bearing, we can calculate the shear stress and the shear force at the bearing using tau is equal to mu times du by dy at the wall. And once we know the shear force, we can multiply it. We can find out the torque by multiplying it with R, and then the power by multiplying it with omega. So after finding out the shear stress, we find out the shear force, then the torque, and then the power. This was a very drastic model that we used, in which we used one step. We could improve the model by considering a very large number of steps. We can take each step of length dx and calculate by equating the flow rate through each of those parallel walled channels. And if we do this, we get a pressure profile like this. In this, the maximum pressure is equal to omega R L divided by 4 B square occurs at 2/3 the length from the left end. B is the average depth of the channel. The velocity profiles through the channels look like this. At the first end, where we have a positive pressure gradient, we have a velocity profile that looks like this. Compare it with the velocity profile that we have drawn earlier for positive pressure gradient. At x is equal to 2L by 3, the pressure gradient is 0. And so we have a straight line profile. In the later third of the channel, the pressure gradient is negative. And we have a velocity profile which is typical of the negative pressure gradient. The force that this bearing can support, the thrust, is 0.1586 into mu omega R L square divided by B2 square. This is not very different from the estimate we made by a very crude model of the bearing. Of course, we notice that F prime increases as mu increases, as the viscosity of the fluid, lubricating fluid in the bearing increases, the load that the bearing can support would increase. But there would be a cost. This larger mu would result in larger shear stresses, larger torques, and larger power lost in rotation. Let us now do one more example. Steady laminar flow through a horizontal pipe. Consider a very long pipe of radius r. Of course, the cylindrical polar coordinates would be preferred coordinates here. So we take z coordinate along the axis of the pipe, and we measure the r radial distance from the center line. We assume there is no swirl, that is, the tangential component of v theta is absent. The cylindrical symmetry suggests that the velocity profile should be axially symmetric. That is, del Vz by del theta would be 0. In a very long pipe, it is reasonable to assume that the velocity profile does not change from section to section and the flow is fully developed. We had discussed this in an earlier lecture too. To find out the velocity profile, we consider a small ring-shaped control volume as shown. A ring of radius r and thickness dr and of length delta z. And we draw the forces acting on this. There would be pressure forces on the flat faces of the rings at the two ends, and the shear forces on the lateral surfaces of the ring. On the inner surfaces, the shear stress would be towards the right because fluid inside this ring would be moving faster than this fluid, so the shear stresses would tend to pull it towards the right, but the shear stresses on the outside would be to the left, trying to slow it down. So we write the forces. The pressure force on the left ring face would be the pressure at that location P times the area of that ring, which is twice pi r delta r. The pressure force on the right ring face is negative and is obtained using the Taylor series expansion of the above result in the z direction. So it is minus P plus del P by del Z into delta Z multiplied by twice pi r delta r, the area of the ring face. Shear force on the inner surface is mu delta W by delta R multiplied by the area of this, and the area is twice pi r delta Z. The circumference twice pi r and the length delta Z. Shear force on the outer surface is obtained by Taylor's expansion of this alone. Now, notice that R also varies. So, we make a Taylor's expansion in which we take this whole expression. So, here delta W by delta R is changing as well as R is changing. WR represents the velocity in the Z direction. Now, since the velocity does not change in the fully developed part of the flow through a pipe, there is no acceleration of the fluid. The velocities at any location Z are the same, so there is no acceleration. Convective acceleration as well as the temporal acceleration, del W by del T. So, the sum of all the forces should be 0. So, if we take the sum of all these forces, we get this result, and this now is the equation that governs the flow through a pipe, a fully developed steady flow of an incompressible fluid. This could be obtained alternatively from the Navier-Stokes equation written in the cylindrical polar coordinate. The momentum equation in the cylindrical polar coordinate is relevant here is only the Z equation, because the only velocity component is W, that is Vz, and it is a function of R alone. So, the second equation here is the Z component of the Navier-Stokes equation in the cylindrical polar coordinates. This is the continuity equation, and with the fact that Vz is a function only of R and there is no Vr and V theta and the flow is steady, this equation is automatically satisfied. Now, here this term is 0 because the flow is steady. This term is 0 because there is no u component, that is component in the r direction Vr. This is 0 because there is no v component, v is V theta, the swirl component. This component is 0 because W velocity, though is non-zero, but it is not varying with Z. This is the body force term, and if we neglect this, we say the pipe is horizontal, then this can be neglected. Delta P by delta Z remains. This term remains because W is a function of R. This term is 0 because W is not a function of theta. It just does not change in the circular direction and it does not change in the Z direction. So, this is the only part of the equation that remains. Simplifying, we get it this. Now, this equation is handled in the same manner as the corresponding equation for the co-ed flow. We know that this is a function only of R. W is a function of R, so this would be a function of R. On the other hand, this P is a function only of Z. P does not change with theta and R. So, this is only a function of Z. One part is a function of R, the other part is a function of Z. The only possible way is if both of them are constant. So, we take minus P prime by mu as constant, that is we take the pressure gradient along the Z direction to be constant, or the pressure to be linearly decreasing in the z direction, and then we can integrate this equation to get a variation of w, the z component of velocity with r. This has to be solved with boundary condition w is equal to 0 at r is equal to capital R, the no slip condition. At the cylindrical wall, the velocity should be 0, and that the maximum velocity at the center of the pipe, that is dw by dr, is 0 at r is equal to 0. With these two conditions, if we solve this equation, we get the parabolic velocity profile. W is equal to minus p prime r square by 4 mu into 1 minus r square by capital R square, where capital R is the radius of the pipe. The famous parabolic velocity profile. We have earlier determined the average velocity. This is the maximum velocity, W max or V max, as we noted earlier, capital V max. And V average is 1/2 of this. The average velocity in the z direction is minus p prime r square by 8 mu. The minus sign because p prime has to be negative for the flow to take place towards the right. We can find out the volume flow rate like we did before. dq dot is equal to the value times the velocity through the ring twice by r dr, and integrating we find out the volume flow rate as pi r4 by 8 mu into minus p prime. This is known as Hagen-Poiseuille law. We have assumed the flow to be laminar and fully developed. Fully developed is an assumption we made explicitly. Where have we made the assumption that the flow is laminar? We made that assumption when we wrote that the shear stress is mu times the velocity gradient. That is valid only for laminar flow. Turbulent flow, the shear stress is much more complicated. So this Hagen-Poiseuille law is only for when the flow is laminar and the flow is fully developed. Notice that we have said earlier that laminar flows through pipe is a rarity. Most commercial pipe operations use turbulent flows. Also, when the flow is laminar, the developing length of the flow, the length through which the flow develops, is quite a large value. It could be up to 100 times the diameter. So the validity of Hagen-Poiseuille law is for a very limited range of applications. Flow through capillaries is one such. We would deal with the flow through pipes for laminar and turbulent flows later in much more details.